Again, I'm going to record the Zoom lecture with the sound. That means you have to choose which sound you want to listen to, Echo 360 or Zoom. Echo 360 supposedly works fine. If not, please call. And let's just do physics. Another example on tracing the electric potential. And it's not a question to answer on the web assignment. No, just a question to practice. And when you look at the circuit, your first step is, and step means you're doing some strategy, and that's what physics is about, strategy. You see a circuit, you don't think, okay, the linear momentum of the system is conserved. No, you see a circuit and you think, okay, there are potential electric currents, and the first step is choose the zero potential somewhere. And the clue is, well, you have a battery. The battery has a negative terminal. That terminal always can be set to zero potential. And relative to this choice, now this electric potential will be equal to 12 volts. And as we know very well, wires do not change electric potential, so electric potential remains the same all up to here, still 12 volts. And for now, that's all we can do with this side of the circuit. Because as we know, with not zero electric current is not zero here, because the circuit is complete. Electric current travels. What we know is potential difference between these two potentials should be equal to current times resistance. But since we don't know, well, that's all we do. So we go to another side. We can trace electric potential here, 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 here. So electric potential here is 12 volts. And now we read it, okay. We got a circuit, and this is what actually we're looking for. So these numbers, what do they say? They tell us how potential changes across this element. So potential changes by 2 volts, but in what direction? Well, we know, well, first of all, we can read, yeah, but we see a minus, we see a plus, but technically we don't have to see those, because as we know, electric current travels in the direction from high potential to low potential. So this electric potential here, I'm saying potential. Yeah. Again, we have to keep track of what we say. There is potential difference or voltage. So electric potential here is higher by 2. Plus minus 0, 0. Why did I say 12? I don't know. Friday is a little Saturday. Yeah, so certain portion of a brain doesn't work already. So 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. And by the way, I know why did I say it, because I looked at this number and my brain made me think that's the right number. The good thing, I can kind of fight sometimes against my brain, and you should be able to do that too. So this is not 12, this potential is 0, and it remains 0, 0, 0, 0, 0, 0. And now this should be 0 plus 2, which makes it 2 volts. And this electric potential remains the same all up to here. 2 volts again. And now what we see is here that electric increases by 8. So from 2 to 2 plus 8, 10 volts. And 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10. Now we know this electric potential should be equal to 10 volts. So this voltage is equal to 12 minus 10, 2 volts. Well, and this is supposed to be what? A resistor, a passive element. Electric current travels through it down. Again, remember, we talked about the directions. It's important to review the direction of electric current has different names. This is we call to the right. This is we call down. This is we call to the left. This is we call up. But in a circuit, it is clockwise. So an electric current goes from high to low. It's a passive element, does not change nothing. And it means this is some kind of a resistor. That's the answer. And another similar problem. And now you know what to do. So I want you to do exactly the same type of reasoning, use this strategy, and tell me the number for the voltage across this element now. How do you tell me? Well, you could call, you could join back Zoom just for a moment, type your number and leave it again. And again, remember, every time when you have a question, you can call or you can join the meeting, ask or type your question, and then leave the meeting again. In fact, now this large monitor actually is much more visible for me. I can easier see if someone writes something, okay? Thank you, one single student who's still in the Zoom. And I hope everybody else is on Echo 360, which means it works. Whew, that's a relief. Now let's see what's happening on the other side. So again, please finish the reasoning, follow the strategy, and inform me using any means available about the voltage across this element. It's not a web assignment question yet. There will be. Okay, web assignment is working. Friday is a good day. So anyone? The main monitor sometimes flickers, gets dark for a fraction of a second. It doesn't bother me because I can see that this, the projector doesn't. Someone joined? Okay, please type your answer or say it out loud. Or someone might have been late. Remember, I told you that I planned to use Q&A session today, but it depends on how much time will be left. So someone has to do something to speed up this process. There is sound. Unfortunately, since there are only 2 students in Zoom, you can't really communicate in breakout rooms. Maybe I'm gonna need to make 2 different Zooms. One for you to check. Hello. If you joined Zoom, please type the answer to my question. Thank you. That is absolutely right. So very, very quickly, let's do it again, because the strategy is the same. The lowest potential set to 0, and the wire does not change potential. Potential up to here is 0, but potential changes by 6. So 0 plus 6, that makes this potential to be 6 volts, and wire does not change potential, so 6 volts remains up to here. And now here we should have potential higher by 8, and 8 plus 6, 14 volts is the potential on this end. And now we go to another part, and the potential here is relative to 0 equals 12 volts. 12, 12, 12, still 12. So the voltage, which is 12 minus 14, magnitude 2 volts. But now there is a slight difference. You see, electric current still travels down through this element. But as we know, inside the resistor, electric current should travel from high potential to low potential. But this electric current travels from low potential to high potential. So this is not a resistor. And actually, thank you. You can leave now until I will ask next question. So if it's not a resistor, what it is? Well, it could be only a battery. If it's not a passive element, it's an active element. We have only 2 kinds of elements: passive or active, resistors or batteries. So if it's not a resistor, done. All right. And this is the web-assigned question. So please take your time, take a look at the circuit, and choose your answer to this question. We have 1 battery, 1 active element. We have 4 resistors, 4 passive elements, first, second, third, fourth. And the question is about the resistor number 1 and the resistor number 3. What type of a wiring do you observe for these 2 resistors? And of course, we have only actually 3 choices: series, parallel, neither. This choice naturally doesn't make any logical sense at all. So please don't choose that. All other technically could have some justification even if they are wrong, but this has no justification at all. 3 is correct. It is definitely at this point not in parallel. Why? The battery messes it up. I could have redraw this circuit in this manner. So I could kind of make this wire longer and this wire shorter and physically move the resistor in parallel. It would look like in parallel, but it isn't, because this battery, an additional element, makes voltage here and voltage here different. And if the voltage is different, they cannot be in parallel. This and this and this are in parallel. Voltage, voltage, voltage is the same. Okay, different voltage, not in parallel. What about electric current? Well, we see a junction. Electric current that travels through this resistor, then splits. And because it splits, electric current through this resistor and through that resistor 1 and 3 is different. And if electric current is different, that cannot be in series, done. So excluded, 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 none of the above. Well, but the solution, of course, is rather simple, because we know what to do. We've done it with capacitors. We've done it with similar circuits with just less elements. We need to simplify the circuit. To simplify, we have to search for elements that connected in a specific way. We don't like this. We like series or parallel. And we can see these three are in parallel. And because they are in parallel, we could replace these with only one resistor, R equivalent. And for a parallel, don't make a mistake, okay, 1 over R equivalent should be equal to 1 over R1 plus 1 over R2 plus 1 over R3. Good thing they all are identical. In general, for any number of identical resistors connected in parallel, the calculation is very simple. In this case, it's going to be equal to just 3 times 1 over 15. And R equivalent will be just 15 over 3. We have to flip it. That gives 5 ohms. And now we can draw a simplified circuit with only 2 resistors, R1, which had resistance of 3 ohms, and this new equivalent, 5 ohms. Again, I made them look like they're connected in parallel, but they're not. Electric current is the same. They are connected in series. So, well, actually, right now I can just do the Ohm's law. All right. In my mind, what did I do? I combine these two in one, and now I have everything I need. The simplest circuit, electric current will be equal to 24 over 8, 3 amps. And this electric current travels where? It's important. It travels through the battery, it travels through this resistor, it travels through this equivalent resistor. I. Actually, in this circuit, see, from plus back to minus, electric current travels counterclockwise in this circuit. Here it travels to the left, and here it travels up. And well, here it splits. How? Evenly. For even same resistors, electric current splits evenly. So it's going to be I over 3, I over 3, I over 3, which gives 1 amp. Then it combines again into 3 amps. And what can I calculate? Voltages. For example, this voltage, delta V1, should be equal to current and resistance. So current, which is traveling through this resistor, 3 amps, times the resistance 3 ohms, 9 volts. Okay, moving on. Next question to you on the Weber sign. So if you think that the current traveling through the top resistor is equal to 5, choose 1. If you think the current traveling through top resistor is less than 5, choose 3. If you think it's greater than 5, choose 2. I don't know. I don't care. I am still sleeping. I need more coffee. What day is today? Out of all these possible answers, the last is irrelevant. It doesn't matter what day is today. What matters is how you understand the circuit. And well, first of all, we need to use our visual ability. Electric current through the resistor on the left is given, and it is 5 amps. And this is what we call a junction, a splitting point. And electric current splits. How does it split? Evenly? No. It would have been split evenly if we had even same resistances. But because the resistance is different, which current will be higher, which current will be lower? Well, electrons are smart. They hate each other, but they are smart. So when they see less resistance, they try to go there. So less resistance, more current. More resistance, less current. So I can call it I2, I3, I1, which is just I. And I know that I2 should be higher, greater than I3, because R2 is less than R3. R2, R3. But that's not the question. The question is, how do I relate I2 and I? And the answer should be obvious by now. Splitting means less current goes through there, because some portion of initial current goes through a different resistor. So the answer is less. And this is 5, so less than 5. Well, what actual value of it? Well, first of all, actually, before we go to that, let's write what we can, because that's always a good thing to do. What can I write? Well, the junction rule, I should be equal to I2 plus I3. Will I use it? I don't know. And I don't care. I care that I have it. And that means if in the future I will need it, I will use it. Well, now what do we do? Let's write what we can. Again, what can I do? Well, we need symbols, right? Notations. Any circuit is being solved by application of the Ohm's law. If delta V equals I times R, and we need to apply to all elements. So if I want to apply to this element, I have to use this delta V1, this delta V2, and this delta V3, but they are the same because these are connected in parallel. Now we know. What else do we know? We know, well, that if I add delta V1 and the delta V2, what should I get? Well, let's trace a potential. Potential, 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 potential. Potential drops here by delta V2, but then it goes up to here. So this should give me 16 volts. Delta V1 should be equal to I times R1 or 5 times R1. And that's actually what we are looking for. If only we knew this is 5. Potential number 1. Well, we need more information. We need to do something else. What can we do? Well, we can use other two resistors yet. We can write the equations for them. Delta V2 is equal to I2 times R2, which is I2 times 2. Delta V3, which actually is the same as delta V2, should be equal to I3 times 3. See how many equations we have. What else can we do? Now, finally, if we want to, we can simplify this circuit. Because now we know we could replace these two resistors with one, R23, and 1 over R23 should be equal to 1 over 2 plus 1 over 3. And now what can we write? Well, we can write that now the same electric current I, which is 5, travels to this equivalent resistor. This will be delta V23, but because it's the same parallel connection, it should be equal to delta V3. It should be equal to delta V2. And because of the Ohm's law, delta V23 should be equal to current times resistance. And because now you know everything, you know the current 5 resistance, 605, done. You can finish and calculate everything. Question. Everybody now uses a lot of devices at home. TV set, charger for the phone, a table lamp, microwave, and in order to use them, you plug every device into power outlet, 1, 2nd, 3rd. So the question is there any specific wiring we could use to analyze your home situation? If you pay electric bill, you should care about this question. If you don't, well, you don't. And you're right, it isn't parallel. What is a power outlet? 2 electrodes. And you have a plug with 2 electrodes. And there's well, 2 wires, they go, let's say, to the bulb. Okay, and the bulb is on. Then you have another power outlet, another plug. Some plugs may have 3 prongs, but the third is grounded, so we ignore it. And it might be connected to a TV, the old one. Some students don't have enough money for the new ones, I guess. They spend it on physics. Okay, and etc., etc. But these plugs, where do they go? Well, every goes somewhere. You actually have a meter, counter, that counts how much energy you use in order to issue a bill to you. And of course, here, the total amount of energy should be just the sum of energy consumed by every single device. So it actually measures how much you spend from one outlet, and then how much independently you spend from, well, we don't touch the wires, so from another, and then from another. So at some point, all those power outlets go to the same points, to the same connection. And that makes all to be in parallel. Numbers, numbers, numbers. And of course, if you know the wattage, the power you needed, and you know how much time you use each device, power times time gives you the amount of work done by electric current, the amount of energy you spend, and then you can add them up all together. And then the total amount of energy you spend in a month, usually, you multiply by your cost. It's in a bill. We used to use joules for energy, but when we pay a bill, electric bill, we use a different unit, kilowatt hour. How many kilowatts you use in an hour? But of course, there's a simple conversion factor. So your bill tells you how much you pay for 3,060,000 joules times the number of kilowatt hours you spend. This is not a Web assigned question. This is a common sense question. If you have, well, it's a common sense question for people who have old bulbs, because new bulbs, LEDs, they have a different type of inner construction. Here, we just have a standard old-fashioned incandescent bulb with a filament. So it looks like this. The filament. And based on the power this bulb consumes, dissipates, provides, the filament may be brighter or dimmer. Well, when we turn it on, at first its temperature goes up until it reaches highest temperature. And when temperature changes, resistance changes. Normally it actually increases, because higher temperature means higher velocity for atoms moving, so more collisions, harder to travel through. So operating resistance depends on the temperature. And what do we know about this bulb? Well, the wattage, we can read it on the top. It says 40 watts, for example. And the voltage, it's also on the top. It says usually 120 volts. Now, again, remember, we talked about it once. In reality, this electric voltage and current changes in time. It oscillates. So this is some kind of an average, or scientifically saying root mean square. And well, power, voltage, and resistance are related. So I can solve this equation for the resistance. Simple. Twice. But what I see is more power, less resistance. So the answer here is which has higher resistance? More resistance, less power. So this should have more resistance. So let's actually calculate. So at least one. The resistance of 100, it's easy, should be 120 squared over 100. 100, so 144.00 over 100, 144 ohms. And you can calculate the resistance of another bulb, 360. 40-watt bulb, higher resistor. Now question. This is a common sense question. You are at home and your roommate is in a different room and well, you are in charge, so you have a 100-watt bulb in your room and your roommate has a 40-watt bulb. You do your homework, you need light. Which will be brighter? I expect that everyone answered correctly, 100% correct answers to this question. We could reverse this question. We could ask, okay, this is my lamp. You see, it says 100 watt. And this is your lamp, and it's dimmer. So which one has more wattage? The brightest or the dimmest? The brighter or the dimmer? Question number 5. Why is the distribution? We just solved the problem. You've got two bulbs. How we connect them? How do we connect them? In parallel, they go connected to the same meter. Everything at home is connected in parallel. 40 watt, 100 watt, power equals 40 watt, we don't even have to calculate it now. Power equals 100 watt, more power, brighter. There's only one correct answer. 100 watt bulb is brighter because at home everything is connected in parallel. What about serious? This is not a WebAssign question. Well, now we have to actually solve this problem. Let's say we did something different. We rewired our own apartment. We've got 120 volts, and now we have two bulbs connected in series. Why? Because we love physics and love doing experiments. Let's say this is the bulb we read on the top says 40 watts. This is the bulb we read on the top says 100 watts. Well, but the brightness, BR brightness, is proportional to the actual power, not the one written on the bulb. So what we need to calculate now is the actual power, P actual for a 100 watt bulb, for a 40 watt bulb. And how do we do that? Well, it actually is easier first to recognize And because they are in series, they should share the same electric current. In this case, power is equal to, well, it's always equal to different. We have three expressions, but the easiest one, current squared time resistor. So 40, 40, same current. 100, 100, same current. But what do they have different? Resistance. Several slides ago, we got it. That was 360 ohms. This was 144 ohms. So which bulb has now higher actual resistance? This one. And it will be brighter. We could actually calculate electric current because electric current should be equal to total voltage divided by total resistance, which is 360 plus 144. And now it's time to play with bulbs. Yesterday on the piazza, someone asked a question. Could we do more examples with bulbs? And I said, I don't remember what I said, but what I want to say now, be careful what you wish for. All right. Late, because they will be late. And this, what you see, is the screen. I will want also an alternative view. On Zoom, just in case. So first of all, let's see what we have here. The plug goes into power outlet, and here we have two different sets of, which says in parallel. You can see red wire goes to one electrode and then to another electrode here, and black wire goes here and there, parallel. Now I can read 40, 100. Parallel means 100 should be brighter, much brighter. 100. Okay. But here we've got the same situation, 40, 100. But now they connected in series. You can follow the wire. Black wire goes this and then to the next bulb, and then it comes back or through the switch. And now you can see 40 is much brighter, 100 is barely lighting up. So what should we take from this? The actual power of a bulb is responsible for brightness, not what is written. If we rewire bulbs in any way, if we need to figure out how bright something is, we need to calculate the actual power, and then more power, brighter bulb. All right, moving back. That's the answer. And now question to you. I have more bulbs to play with. I'm going to prepare this circuit. And here, what we have is a bulb. It is connected to a battery. I'm going to switch soon. For now, just checking. Okay, it does work. Okay. Now I need a switch. Well, for the switch, I could use just a wire. This switch, this wire, will be connected to the bulb parallel to it, like this. And what's going to happen? Switching. Shut the left. Two. Zoom. So again, the battery connected to the bulb. Good, simple circuit. Now this is my switch. I need to close it. So, it means I need to connect it to this electrode. So what's going to happen at the moment of truth? Why? Volume, capture, zoom. We actually already have answered this question in a way when we solved the problem about 3 resistors. Remember? When we had 2 resistors connected in parallel, R2 and R3, and R2 was less than R3. So we said the electric current here will be higher. Less resistance, more current. That's natural. And in our example, we do what? We do this. So R2, let's use the same symbols, R3. But what is the resistance of R2? It's a wire or a switch, and the wire has no resistance. So no resistance, 0. What does it mean? It simply means that now all electrons will travel through this, and no electrons will travel through that. Electrons are smart, not stupid. If there is no resistance, they all go there. All right. So a couple of more similar situations just to analyze briefly. It's not an, well, I could do, but we understand what's going to happen. Now, in this circuit, electric current travels through 2 bulbs. Same bulbs, so equally bright, but dimmer than in this circuit. If I close the switch, well, right now the switch is open, so it's bright, but it's only 1 bulb, 2 bulbs more resistance, dimmer. If I close the switch here, as we did, all electric current goes there, this comes dark. If I close the switch here, what's happening? Now all electric current goes like this is dark, this becomes brighter. What's happening here? This situation is identical to that situation. I close the switch, all electric current goes through this switch now, no electric current goes through those bulbs. More bulbs. Well, we need to calculate the voltage, and also we need to answer what is happening about the brightness. By the way, by now everybody should know, because this was a question basically in your lab. And actually first, let's take a look at another realization of this experiment, and then we will analyze it. So I have here 3 bulbs. At first, I will connect only 2. I can see 3 bulbs. Capture. And right now, they are not connected to anything yet. So this is what I want to use. Connect 1 wire to this electrode, second to this. So what's happening? Well, there's a power outlet, and these 2 bulbs now connected in series with each other. This switch, if I turn it on, will connect this bulb in parallel to this bulb. These 2 bulbs will be connected in parallel. And what's happening? That bulb alone becomes much brighter. These 2 becomes dimmer, but equally bright. Turn it off. So this bulb is not a part of a circuit anymore. Again, equally bright, but dimmer than this bulb when the 3rd bulb is a part of a circuit. Of course, it's all about actual power for each bulb. And in order to analyze actual power, what do we need to do? Calculate it, or at least pretend that we could calculate if we knew all the values. And it doesn't matter if we know numbers. What matters if we know the relationship, if there's the same or different. Of course, first we need to redraw the circuit with only 2 bulbs. If the 3rd bulb is not a part of a circuit, why do we have to keep it? So we've got 1 bulb, we've got 2nd bulb, and we've got the battery connected. That's it, nothing else. So the voltage, resistance 1, resistance 2, electric current travels from plus to minus, so electric current in this circuit travels clockwise. Electric current through each bulb travels to the right, and this electric current I will be equal to voltage to the total resistance, R plus R to R. And if I want to calculate the power of the bulb A or the power of the bulb B, because in this situation power should be the same, what should I do? Well, I should choose the best, the easiest relationship. And for that I would use voltage and resistance. The voltage number 1 of A is equal to the voltage B, and it means the total voltage splits evenly. So A is equal to B, which means 1/2 of the total, or 6. So because I know voltage and resistance, this is my equation I would like to use. Well, technically I have to write delta VA squared over R. Why is it R, not 2R? Well, 2R is the resistance of 2 bulbs. I'm calculating power for 1 bulb, A, so I have to use the resistance of that bulb, A, and that's R. Okay, we know that the voltage, individual voltage, is 1/2 of the total. So 1/2 squared 1/4 of the total voltage squared divided by the resistance of 1 bulb. Done. Now we close the switch. A different circuit. Bulb A, bulb B, bulb C. Same original voltage across the total circuit. Electric current now should be what? First of all, where? By adding an extra element in parallel, we are decreasing the resistance. We give electrons more room to travel through. If we decrease if we decrease the resistance of a part of a circuit, we decrease the overall resistance. When resistance goes down, electric current goes up. So right now, the new electric current through bulb A, the new one, should be higher than it was with only 2 bulbs immediately. And we can calculate, of course, how much higher. But at this point, that's all we need. Because now if I want to calculate the power of A, now I actually could use this current squared times resistance and compare with the power of A old current squared times resistance. Higher current, same resistance. Lower current, same resistance. So new power for A is higher than old power for A. That's why it goes brighter. But then that electric current splits. So we would expect for B and C power drop, and that's what happened. Now let's just do coefficients, numbers, and for that we have to do mathematics. So first we need to redraw the circuit, make it simpler. This is A, and I can replace these 2 bulbs with one resistor RBC. What should be equal to? If you have 2 identical resistors, the equivalent resistor either twice more or twice less. We just said by adding in parallel, we decrease the resistance, so it should be equal to 1/2. Of course, you can calculate it literally by applying the rule. And now we have to apply the same voltage as before. So what do we see here? Well, we see that now the voltage A star, the new one, and this voltage BC are not the same. Which will be higher, which will be lower? Well, now in this circuit, they share electric current is the same. So same current, more resistance, more voltage. I can write it down as an Ohm's law. Delta VA star should be equal to electric current new one star times resistance. Delta VB star, actually I don't need star here, it's just BC, will be equal to the same new current times the equivalent resistance. And by the way, actually, I can immediately see from this calculation that electric current, because the electric current is the same, the voltage A star will be equal to twice. I have to multiply by 2 the voltage BC to get IR. Plus, I also know that the voltage A star plus the voltage BC should be equal to total voltage. This is not the only way to do it. I don't show you other ways because we've done it before. We could apply Ohm's law to each element. But this is also a neat way to analyze what's going to happen. And what's going to happen? See, simple mathematics. This plus twice of that equals the original voltage. So 1 plus 2, 3. So this voltage should be equal to 1/3 of the total. This voltage should be equal to 2/3 of the total. 2/3 plus 1/3 gives the total. That's how it works. So we could immediately say, well, if my voltage is 120, the numbers for each voltage. And what does it say? This voltage should be equal to 1/3 of the total. The new voltage for A valve should be equal to 2/3 of the total. So now I want to finish this problem by tracing the potential. First of all, now with each voltage, so delta VA star, delta VBC, delta VBC. Of course, we can calculate each power, PA star. We can use current voltage, doesn't matter. Delta VA star squared over R. PB will be equal to star, new one, will be equal to PC star, will be equal to this voltage, BC squared over R. And as we just said, now let's use numbers. Because total voltage is 120 volts, this will be equal to 2/3 of 120. Which is what? 80. And this is equal to 1/3 of 120, which is 40. And it says trace the potential. Let's trace the potential. Again, I just want to redraw it so it would be clearer. So this is plus, this is my battery, plus minus. So, of course, the lowest potential is at the negative terminal, and we got 0, 0, 0, 0, 0, 0, 0, 0, 0 potential here, 0 volts. But now, potential should rise, increase by what value? By 40 volts. That means electric potential here becomes 40 volts. And of course, electric potential here is 40 volts. And here is still 40. And electric potential here is what? 120. And of course, it makes perfect sense because this is electric potential, but potential difference, again, is 80. Everything fits. Well, these are answers, and we just finished it, and I just did this, and I just finished that. I said that, and that was done. This closed switch, I would say just again, brightness of A is greater than brightness of B, but brightness of B and C is the same. That's the answer. And these are potentials. What did I do wrong? I did wrong math. It's Friday. No, I didn't. My math is correct. So I do have different numbers. Maybe this slide from a different voltage. I have to check. Oh, that's a different, yeah, I didn't do that. So the circuit on the right, I finished 40 and 180. I didn't do the circuit on the left. That's why I get confused. But the circuit on the left is a circuit with only 2 bulbs in the circuit. So the voltage of 120 evenly splits. We've got 0 and then 60 and 120. Done. All right, another question to you. Yeah, maybe we'll not have time for Q&A. In that case, you will use Piazza. What's going to happen if I close this switch? Well, this situation is actually identical to the case we've done before with only 2 bulbs. The battery, the bulb, and everything depends on how we connect it. And if we connect it in parallel, the connection in parallel does not affect the brightness of this bulb. So I can close the switch, I can open this switch. Whatever is happening on this side does not affect anything on that side. So it will remain the same as before. Of course, switch open, switch closed, different circuits. But what will be different? Well, now let's analyze. When the switch is open, that problem was solved for this part. We've got electric current traveling through 2 identical bulbs, so this potential evenly splits. But we've got the same situation on the left. This potential evenly splits, 60 volts, 60 volts, 60 volts, 60 volts. Everything clear. Electric current provided by the battery will be this current plus this current. And if I close the switch, it doesn't affect the left side, but it affects this side. By closing the switch, I decrease this resistance. So I decrease overall resistance on the right. And by the way, that means I decrease overall resistance of the whole circuit. That means total electric current increases. But now it splits unevenly. Less resistance, more current goes here. Same resistance as before, same current as before, goes there. And what's important is, it is just a picture. In the picture, this is on the left, this is on the right. In real life, it is completely up to us how we choose the orientation of the bulbs. could have been like this, battery left, right, could have been like this, battery top, up, but it could have been like this. It doesn't matter how I move elements and wires. It does not affect anything physically. It is only in our mind. So, an actual wire is always flexible. That means I can redraw any wire in any way. I can redraw any circuit in any way. What do I need to preserve? I need to preserve the connection. That's it. If these are in series, they must remain in series. If these will be in parallel, they must remain in parallel. That's it. And again, if we trace the potential, set it to 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. And 120, 120, 120, 120. Now, in this situation, voltage evenly splits. Voltage is 60. So this potential is 60 plus 0. It is higher by 60 than 0. Or it is lower than 120 by 60. Voltage splits evenly 60, 60. Same here, 0, 0, 0. And then 120, 120, and even splits, potential 60. And I'm going to do it here. If we've got, actually, you know what? You see what I want to do. I'm going to close the switch. Okay. But as I said, who cares where these bulbs are actually located? So I can move those two bulbs from left to right, but I have to make sure the connections are the same as before. So this should go to the positive electrode, and this should go to the negative electrode. That's it. So this potential is 0, 0, 0, 0, 0, 0, up to here, 0 volts. And also along this wire, potential 0 volts. This potential is 120, 120, 120, 120, 120. And voltage splits evenly by 60. So this potential is 60 volts. And we've done before 0, 0, 0, 0, 0, and 120, 120, 120, 120. But now the voltage doesn't split evenly. Now this voltage should be twice than that voltage, and it gives 80 volts and 40 volts. Twice higher, but together 120. There are only two numbers that satisfy this condition. In mathematics, this is a system of equation. X plus y equals 120, and x equals 2 times y. Only x is the voltage number 1, and y is the voltage number 2. All right, so answered. Did it? No time. I just traced the voltages, but now we just have to do it backwards. In this problem, I know potential difference here, the voltage here, and if this voltage, let's call it B, is equal to a certain value, and this voltage, let's call it A, because a wire doesn't change potential. This potential is B, this potential is A, this potential is B. Up to here, this is all potential B. This potential is A. Up to here, this is all potential A. So potential difference here, V A minus VB magnitude will be equal to 10 again, same value as here. And in this situation, the bulb number 3 does not matter. So we can redraw the circuit having in this circuit only bulbs that matter. And we know that the voltage across the bulb number 2 equals 10 volts. And we know these bulbs are all identical. And that means the electric current is the same. And the voltage across each bulb is supposed to be the same. This voltage should split evenly between all these 3 identical bulbs. So it immediately tells us this voltage should be 10 volts. This voltage should be 10 volts. So this EMF should be 10 plus 10 plus 10, 30 volts. They all should be equally bright because same resistance, same voltage, same current, same power, same brightness. Done. So I just did this, I found it 30 volts. And if the switch is closed, but the voltage number 2 is still 10, how can we achieve it now? Well, we need a different battery. The question is, what should be that different battery now? Well, again, now I can redraw the circuit, keeping only 3 elements. This is R, this is R, and this is what? What one resistor could use to replace these 2 resistors? What equivalent resistance? Well, we know the rule. For identical resistances, resistance could be only doubled or cut in half. For connection in series and doubled, for connection in parallel, it's cut in half. So this equivalent resistance should be equal to 1/2 of R. So what does it mean? Well, with electric current the same, if my voltage here is 10 volts, this voltage should be twice of that, because the resistance is twice. This voltage should be twice of that, because the resistance is twice higher. And now 20, 20, 10, that gives me 50. Could you do it longer? Of course you could do it longer by writing Ohm's law for everything. You always can apply the same law as long as you apply this law correctly, which means in this law, all variables supposed to be to the same element, the same element. So you can write this law once, twice, 3, 4 times. Then 5th time for this resistor, and then at least 1 more time for the whole equivalent resistance of the whole circuit, R equivalent. So this is how many times you can write this law. So it could have been a very long calculation, but if you know the physics, the reasoning is quite fast. All right. Bulbs are identical. Rank them in terms of brightness. Brightness proportional to power. Power is proportional to current squared and the resistance, or V squared over resistance, because they all have exactly the same resistance. All we need to know is either current or voltage. For example, if I don't know yet, if I1 is greater than I2, then brightness 1 should be larger than brightness 2. That's if. Or, again, another if, a hypothesis. If, let's say, and I'm going to use just V for voltage, V1 is greater than V2, then brightness 1 is supposed to be more than brightness 2. Those are ifs. So our goal now is actually just to figure out and rank all currents or all voltages. Well, I usually start from voltages and see if it helps. So what I know now is here, voltage 1 actually equals voltage 2, for sure. Here, voltage 4 is equal to voltage 5, because this voltage 6 splits evenly between 4 and 5. So 6 will be twice then 4, 4 twice then 5. All right, what else do I know? This voltage 3 is a part of it. Now, I have to simplify. I have to do some simplifications. So, what can I replace? I can replace bulbs 1 and 2 with one bulb that has a half of resistance. We've done it several times before. This is bulb number 3. Now this. So this is trickier. So first I need to simplify at the top. There's going to be 2R and just an R at the bottom. Section. Okay, still what do these are in parallel, so I want to replace these, and that should be equal to 1 over 1 over R plus 1 over 2R. Now, I told you in PY105 a little trick. When we know for sure that an actual value of something does not matter, we could set that value to a convenient number. For example, I don't know the battery. I could set it, I don't know, 120, why not? For brightness, for ranking, it should not matter. What else could I do? I could choose a convenient value for R. I could set R to be equal to, I don't know, 6 ohms, I don't know. Yeah. And of course, now everything might come easier for us because now we just can calculate everything. But in general, of course, we don't have to do that. In general, we could just analyze things as they are. So what's going to be 2 over 2? 2 times 1 plus 1, 3. So 2R over 3. That's the equivalent. So this is my next circuit. 1/2 R, and 2/3 R. When I have a circuit when everything is in series, now I know how to relate all the voltages. For example, this my voltage, I just call it V, because I have EMF here. Okay. It's different from voltage V1 or V2 by how? Same current, twice resistance, twice voltage. So this voltage should be twice higher than this, so this should be a half of that. Moving on to the next part. Same electric current. That means this voltage should be proportional to this with the same coefficient, 2/3. 2/3 of V. This is what? This is what I call the V6. V6. This is for this part 6. This one. 6. V. V1 or 2. But now what do we know? Well, I know that if I add them all together, V 1/2 of this plus 2/3 of this, that should give me total EMF. Of course, first of all, what you see, the actual value of R does not affect voltages. The distribution doesn't depend on actual R. Could be 1, could be 10, could be 6, anything. Still 1/2 times V plus 2/3 will be the same EMF. So you could choose a convenient value for EMF, solve it for V, and that automatically will give you V1, V2, V6. But what we can see now is, well, V1 is equal to V2, we said that. But it's less than V, or we could say V3, less than V3. What about V6? So V6 is less than V3, 2/3 of that. And now if I want to compare 1/2 and 2/3, I want to compare V1 and V6. V1 is 1/2 of V, V6 is 2/3. Which is larger, 1/2 or 2/3? Well, times 3 is 6, times 2, 4, 6. So this is 5. So V6 is greater than V1 over 2. Right? Times 3 times 2. And 2 more voltages, 4 and 5. Well, we know V4 equals 1/2 of V6, so it's going to be 1/3 of V. And 1/3 of V is less than 1/2 of V. So V4 will be less than V1. I have no time, but now you can rank the brightness based on brightness for all bulbs based on the ranking of voltages. Again, as I said, higher voltage, brighter bulb. Lower voltage, dimmer bulb. Well, in this case, that's the answer of this. And with a given number, you can finish calculation. With a given number for EMF, you can finish calculation and calculate each individual voltage. This is done. And I have to stop. Thank you very much. Have a nice day. Post your questions on Piazza. If we didn't have all the technical difficulties, we would definitely have time for Q&A. Have a nice weekend, everybody. Save. Microphone. Zoom.